Hello everyone, I'm Flávia Padovani. My colleague Thiago, Bretas and I'm from BVP Engineering Company, and we're going to present about tailings dam safety assessment considering undrained foundation failure. Firstly, a brief introduction is going to be presented in order to indicate that static liquefaction failure could be linked with contracted undrained behavior. For this, some liquefaction case histories is going to be reported, then a case study for a tailing store facility will be presented. Some stability and seepage analysis were developed using HawkScience software, and the conclusion for the results will be discussed. During the construction and raise phase of the tailing store facilities, some mechanisms could be verified as rapid loading, rapid raise of the water table, and localized deformations. All these mechanisms can function as triggers for undrained shear or undrained behavior, as they can reduce the available shear stress and thus the available strength of the materials. Some case histories can help us to understand better this. Here we have the Los Frailes dam example. It was a rockfill dam founded on plastic over-consolidated brittle foundation clay. During the construction phase, there was noted an increment of pore pressure assigned to the rapid loading. The brittle nature of the clay strength suggested that progressive failure could play a significant role in reducing the available foundation strength during the construction of the dam. Another interesting case is that one of the Mount Pauline dam, which has been partially a drain treatment process. The Mount Pauline tailings store facility were composed by 3 continuous embankments. According to the panel, the failure occurred in the glaucolacustrin layer called upper GLU. This layer was found to be pre-consolidated prior to embankment construction, but became normally consolidated under the loads applied by the construction of the embankment. Given the high stress that acts on the GLU prior to the final construction campaign in 2014, it would have taken only a small additional load to initiate undrained failure. This is consistent with the collapse of the embankment without any apparent warning. And last but not least, we have the Brazilian new context. Since August 2019, when the resolution number 13 was published, the Brazilian National Mining Agency has determined a minimum factor of safety of 1.3 in stability analysis and studies of liquefaction sustainability, considering peak undrained shear strength. The resolution number 13 also sets the importance of developing this kind of evaluation in the studies for dam safety inspection and design. The case study is a tailings store facility built with a compacted landfill and raised by the centerline construction method. The dam has a part of its embankment supported by thin upper residual soil. Below this, there is an altered rock to bedrock layer, as shown the typical cross-section represented here. The mechanical behavior of the residual soil and the tailings under undrained shear was evaluated. For the tailings deposited in the reservoir, the potential for contraction was verified using the cone penetration tests. The typical profile for tip resistance, lateral friction, and excess pore pressure measured during the fusion cone test is presented here. An evaluation of the state parameter was also carried out in the light of Ben and Jeffers' 1985 approach. The state parameter represents the difference between the current state of the soil and the critical state at the same stress. Materials with a tendency to contract under shear have a state parameter greater than minus 0.05. The red line here represents the limit of contractive and relative behavior. The assessment of the tailings understood indicated a very loose in situ condition, since the mean of the values of the state parameter was approximately equal to 0.3. Finally, the data was analyzed considering the modified normalized soil behavior type proposed by Robertson 2016, whose representation is made through the normalized cone resistance UTN by the normalized friction rate FR. The CD equal to 70 boundary represents the contractive dilative limit. So according to the modified SBTN system proposed by Robertson, the tailings have a contractive behavior since most of the points were plotted in the right side of the boundary CD equal to 70. Besides, we can see that the first 10 meters, the tailings were classified as sand-like materials with intercalations of clay-like sensitive materials. In a greater depth, the tailings were in turn classified as clay-like materials. The distribution of the points on QTN by FR original graph by Robertson is shown here. The peak undrained shear strength ratio was calculated using Olson and Stark empirical relationships. The 25th percentile was selected from the histogram data distribution. Jeffers and Bean suggested 20 percentile as a good reference. For the residual soil, the assessment of the CU 3XL test suggested a contractive behavior. As can be seen here, there was a constantly increasing of pore pressure during the shear phase. However, a stress softening response was not verified by the stress-strain curves, since there was no significant strength loss after reaching the peak strength. The effective stress path for the residual soil samples is presented here. To determine the peak undrained strength, it were performed a constant volume direct simple shear test on undisturbed samples. The results obtained by the SES test on the residual soil is presented here in terms of shear stress and excess pore pressure by shear strain. Note that the soil didn't show significant loss of strength after the peak. The mechanical behavior is consistent with the one indicated by 3XL test. So for the point of the maximal shear stress indicated by the red points here, a peak undrained strength ratio of 0.35 was obtained for the residual soil. The geotechnical strength parameters considered for stability and seepage analysis are summarized in the table below.
Hi everyone, my name is Thiago Bretas from BVP Engineering Brazil, and I'm going to present the 2D and 3D stability analysis results of the Tailings Dam. First, it was created a 3D model on Autodesk Civil 3D software, including the topography, the dam's body and its drainage system, the tailings reservoir, and the local geology. This 3D model was fully imported on RS3 software from Rock Science, to generate the water surface that was used on the stability analysis by limit equilibrium. The dam's foundation was discretized into 3 layers, indicated in this model by brown, rose, and pink materials. The tailings reservoir is indicated by the gray volume on upstream. This image presents the seepage analysis results by finite element method on RS3. On the left, it's presented the total head, showing that the reservoir has the highest value, indicated by the red region. On the right, we can see the pressure head on the model, where the blue colors represent the negative water pressure, in other words, the part of the model that's over the phreatic surface. The phreatic surface created on RS3 shows the water flowing through the chimney drain and the drainage blanket under the dam from the reservoir. We can also see the water surface on left and right abutments as well. The 3D model and the phreatic surface were imported to slide 3 for run stability analysis by limit equilibrium. Therefore, the software discretized the sliding mass into vertical columns with a square cross-section, and the equilibrium is calculated on the base of each column, just like the slices methods. The first analysis considered a drained behavior of the foundation, and the results shows a factor of safety of 1.69 by GLE Morgenstern-Price method using Cuckoo search algorithm. This factor of safety is higher than the minimum value of 1.5 recommended on Brazilian and also on international standards. The calculated critical surface covers almost all over the dam's downstream slope, from the crest to practically the dam's toe. Laterally, it was limited by left and right abutments. This image shows the column weight area ratio. The middle part of the failure surface, indicated in red, has the highest depth, about 18 meters. Here, it's presented the column's base pore pressure, indicated where the critical sliding mass intercepts the phreatic surface, generating pore pressure. Likewise, this image presents where the critical failure surface intercepts different materials, showing the column's base cohesion. The sliding mass crosses the dam's body and 2 foundations layers. 2 sections were created to analyze the stability also in 2 dimensions by limit equilibrium. On the left, it's shown the location and the cross-section 1, and on the right, the section 2. We can see the critical surface, orange line, and the phreatic surface imported from RS3, the blue line, on both sections. The 2 sections were exported from slide 3 to slide 2. This image shows the results of section 1 analysis, where the 2D critical failure surface is indicated in green and the 3D surface in red. As we can see, only the 3D surface intersects the foundation in this section, indicating an important difference between the shape of 2 surfaces. The 2D analysis results from slide 2 indicates a factor of safety of 1.61 using Morgenstern-Price method and Cuckoo search algorithm, while the 3D analysis presents a factor of safety of 1.69. In other words, the 3D factor of safety is about 5% higher than the 2D results. This is already expected because the 3D shape effects are not taken in account in a 2D analysis, which considers an infinite third dimension. The section 2 analysis results show a factor of safety of 1.59 and similar surface shapes. The 3D factor of safety calculated is 6% higher than the 2D factor of safety in this section. Now, this analysis considered undrained behavior on the first layer of dam's foundation. The residual soil, modeled with a vertical stress ratio of 0.35. We can see a lower factor of safety of 1.42 compared with the last analysis, which is already expected. This factor of safety is higher than the minimum value of 1.3 recommended on Brazilian international standards for undrained conditions. The results shown are also based on Morgenstern-Price method and Cuckoo search algorithm. The calculated critical surface covers almost all over the dam's downstream slope, from the crest to the dam's toe, and it's wider than the last analysis, touching the abutments. This is the column weight area ratio, indicating the deepest region of the critical surface, the red area, about 24 meters. This critical slip mass is, therefore, deeper and wider than the first one. The critical slide mass has about 143,000 cubic meters volume, while the analysis with drained foundation presented a 107,000 cubic meters volume. This image shows where the critical slip mass intercepts the phreatic surface, generating pore pressure on column's base. Likewise, we can see clearly where the base of the slip mass intercepts the dam's foundation, in this case modeled with undrained behavior of the residual soil. Those are the two sections created to analyze the 2D dam's stability. On the left, it's shown the section 1 location, and on the right the section 2. The sections also show the critical slip 3D surfaces, the orange line, and the phreatic surface, the blue line. The two sections were imported to slide 2 directly from slide 3. The section 1 analysis results show a factor of safety of 1.22, 16% lower than 3D analysis results. Despite the similar shape of surface, in this 2D section, the difference of the factor of safety is considerable. We can also see that both critical surfaces intercept the undrained behavior foundation, the brown layer. The section 2 analysis results show a factor of safety of 1.40, practically the same 3D result, and similar surface shapes, also crossing the undrained foundation. Conclusions. Analyzing only the 3D results, we can say that the stability analysis for drained foundation behavior is okay, with a factor of safety over than 1.5. The stability analysis for undrained foundation behavior is also okay, with a factor of safety over than 1.3. It's important to mention that a foundation failure may be a trigger for static liquefaction, showing the importance of analysis like this. In this case, 3D analysis showed 1 to 16% higher factor of safety, comparing with the 2D results. The 3D analysis is more realistic. The critical surface shapes have difference. The location of 2D section leads the results. Section 1 analysis for undrained foundation behavior, for example, showed the factor of safety of 1.22, and Section 2 showed a factor of safety of 1.40. In this case study, 2D analyses were more conservative, presenting lower factor of safety values. Thank you.